So now I want to wrap it up a little bit by explaining the kind of defects that the models that I was looking at certainly have, and how this kind of would affect, I mean, if you have other models, how that would change the picture. And I call that looking more closely at the process of infections. And so what is, I mean, the dominant, if you have something like corona or also the flu, or so what is the dominant kind of way people infect each other? Of course, let's look at it from the engineering point of view. You are some kind of combustion engine. So this is my little man. He is a combustion engine, and he is pumping in and out fresh air with a lot of oxygen, and he is, of course, producing the product of combustion, which is water vapor and carbon dioxide. And if he is infectious, of course, he is also exhaling virus. And what is happening from the point of view of, I would say, of the physics of nucleation, is you have this hot, well, 37 something degrees water vapor, and you exhale this water vapor together with some virus. So the virus is a minuscule thing, but it's only minuscule, compared, let's say, to bacterium or so. But it's of course huge with respect to the water vapor. And what we are saying is it's an ideal nucleation germ for the water. So a little droplet of water will form around it. And think about this. That's what I explained already. Think about it. That this water vapor which we have there, I explained that already before, this water vapor is increasing, or is able to increase this little droplet, let's say up to whatever, 10, 20 times the diameter of the virus. In that case, you will have produced something which is much larger than the virus, but not that much larger than the virus, still minuscule, but which has basically the specific weight of a water droplet of the corresponding temperature, because the virus is only a very small proportion of the volume. Yeah, that goes with the radius to the 3, you remember. So we will, the way that we are spreading the virus is basically subpopulation NJ and subpopulation NL. They meet with a certain frequency at some meeting points, and these I call VKJ. V is, in graph theory, it's a vertex. So the meeting points could be, for instance, like in carnivore or so, there could be a bar, something like that. And there is, of course, not only one bar, there are many bars. And the process is not a simple mean field contact process, but it is more or less like such a contact process, with the big difference that now the probability that you are going to get infected is actually not linearly depending on the amount of contaminated aerosol that you have, but there is the typical kind of curve which you have there. I would say is not a linear curve, but it's something like such a curve. So I mean, it levels off. Of course, I mean, at one point you have a maximal kind of possibility to get infected, and this here should be the aerosol contamination. So it is just the virus load in the aerosol, but I mean here we have the rate of infection. And of course, this is not exactly the same, what we are doing here, because this will change. So, well, up to which point I can still, I mean, what can I do in order to get to the equations before? I'm not discussing that in detail here. I'm just saying what you have to think about this f of r. This is kind of the relationship between aerosol concentration and the rate of infection at this vertex, which we call this meeting point, which we call f of r. And so the equations look a little bit like before. I didn't write down the equations for the IL. They are not changed, of course. They are just there's a positive rate and there's a rate of quarantining that is still the same. But what changes is that this relationship is no longer a linear relationship. So the dt Sj or the dt of the log of Sj, as I'm saying, is now a nonlinear function of this IL. And unfortunately, in general, what you lose is the simple structure of the invariants which I had. So for these invariants, actually I needed the special, I would call it algebraic structure, which we have here. And that is a general phenomenon in differential equations. Algebraic structure in many cases leads to integrability, and integrability means that you can solve your equation basically by restricting to a level, I mean, these level curves of certain invariants or integrals of the equation. And now you lose that. But what is still the same is, of course, if you look at the points here in this equation where the I of L is is very small. So you look at the stability or non-stability of the Sj. Well, then what you are looking at is, of course, not really this complicated nonlinear expression, but something which is just the derivative of this with respect to I. And the derivative of this with respect to I at the point I equal to 0, that still has the same kind of structure or property that we have here for the that we had for the SIR model. So what is still true is you have the way to reduce by linearization the nonlinear problem to an SIR model, and this SIR model which you have there gives you the same kind of picture in terms of what are the stable Sj and what are the unstable Sj. That is still the same, and you also have the property that when you are in an unstable point, there is a trajectory, so-called heteroclinic trajectory, which is connecting this unstable Sj to a final outcome, which has to be one of the stable Sjs. But you don't have this simple function which was determining basically by its own the function was this kind of set of invariants which I gave there, which was determining by its own what Sj, what unstable Sj connect during the epidemy with the stable Sj to which the heteroclinic trajectory leads. So there is, it's not everything which I'm telling you is universal. Some things are, but some things are not. And I think that will be all I want to say. If you want to learn more about the mass of it, well, why don't you come to Leipzig?